check. Okay. Okay. Hi everyone. So, yeah. Okay. Sorry for the delay. I was just testing the audio. Let me know if the audio works and whether it's fine. And you can hear me well because yeah, I don't have a consistent stream setup. So every time I want to stream, I have to keep testing the audio, making sure it's just nice, not too loud, not too soft, and everything. Okay, so yeah, we're going to discuss the tasks of this Google Code Jam farewell round. As you might have known, Google, yeah, it's an unfortunate news that Google decided to disband or like, yeah, terminate the programs, the coding competitions program, effective immediately this year. So Google Code Jam, Hashcode, Kickstart, they won't have it anymore. Yeah, I guess yeah. If we must speculate why it should be related to the current economic conditions and recent layoffs across tech companies, including Google as well, yeah, it's probably makes sense to focus on something else instead of this program, which I don't know whether it's very effective in their purpose of hiring, but yeah, it's and yeah, because maybe they're not hiring as much anymore as well, so it probably makes sense to terminate hiring programs, including this one. Yeah, and they decided to hold a final farewell contest, which actually is good one, so that yeah, it's not suddenly that we don't have like competitions from them, but at least they still give us something this year, and I believe they already prepare some problems for this year, for different rounds. And yeah, since they already have the problems, I think internally the decision to terminate program is also quite sudden. So yeah, they already have some problems, and then suddenly they decided to terminate. So yeah, they decided to use the problems for rounds instead. And yeah, again, since they already have the problems from different rounds, they decided to make different rounds here as well, depending on the difficulty level and so on. So yeah, I decided to participate in round C. I was deliberating before the round starts whether to participate in C or D, but yeah, in the end, since I was not feeling very mood for like hard problems, like yeah, 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 I don't know whether I can do well basically, like currently, like it's not my prime condition to compete. So yeah, I decided to take part in C instead. I'll of course try to read problems in round D later. But yeah, so yeah, um, yeah. Okay, let's take a look at the problem. So yeah, the result is out. As you saw, Google coding competitions. Some of the problems have hidden tests, which means that your submissions will not be revealed during the contest, but immediately after the contest ends, it's revealed. Yeah, I tried to solve all the problems. I thought I aimed to solve all the problems, but as you can see here, my problem C failed. But yeah, I believe it's just technical implementation because I actually got memory limit exceeded. We'll see when we go through the C problem. But yeah, I guess the main thing is that I know how to solve all problems, at least theoretically. Not implementation wise, maybe there's some issue, but yeah, we'll discuss all of them. And yeah, I keep monitor the chat, so anything, yeah, feel free to post it in chats. And if you want to ask questions or you want me to go slower or anything. Okay. Yeah, so okay, so yeah, the first problem is yeah, this game sort part one, which is basically the first time I see this problem statement. It's actually confusing because there's this integer p. They want to make the problem statement as similar as the part two, but yeah, it's actually confusing because like it says that there's an integer p, but here in this problem p is actually not given at all. Like wait, sorry. No, sorry. P is given, but here has to split as exactly P contiguous substring. So I thought the question was about splitting, but in this problem, actually the split is already done. So this sentence is kind of like confusing for this problem. But yeah, once we like um, if we read the problem statement more slowly and carefully, it shouldn't be a problem. Like, and then if you read the samples and input formats as well, you see that, oh, actually the string has already been split up. You don't really need to split anymore. So yeah, so yeah, and then yeah, I guess yeah. So the question is we are given p strings basically, and we want to arrange this like permute each of strings such that the strings are non-decreasing lexicographical. It the sorting the condition of the non-decreasing lexicographical is not the string itself, but it's like one string compared to the next string. So si cannot be more than, like, strictly more than si plus 1. But there is no condition whether si, the string itself, must be sorted or not. There's no condition on that, right? So yeah, basically take a look at some examples here. Yeah, so basically here this is valid because CO is less than DEJ and DEJ is less than MA. Yeah, you see that MA does not have to be sorted. You don't need to sort it like AM, it doesn't matter. But you must make sure that this string is less than this string, less than or equal to, right? Okay. So yeah, and yeah, this problem reminds me of another problem that was in an ICPC regional before in Jakarta. But the question is, you want there's like k, so n and k, and for each string you have to choose a subsequence of k characters, right? And then yeah, the same thing. The string that you choose, the subsequence of characters that you choose, it's k characters, and then the next one must be lexicographically larger, right? The idea is the same. Basically, we want to use a greedy solution. There is no harm in, for the first string, there's no harm to like choose as small as possible. So which basically means you just sort the string, because that is the minimum lexicographically string possible by rearranging CO. And then the next one, again, there's no harm in like taking the minimum string that you can construct with from this, but not smaller than this, right? Because that is the condition, right? So by creating a minimum possible string from here, you make sure that for the rest of the string you have more possibilities, you have more answer candidate as well. So yeah, that's the idea of the greedy solution. And yeah, how do you generate a minimum lexicographically string that is still larger than a specific previous string? Yeah, you can do a greedy algorithm. Basically, yeah, everything with lexicographically, you can always try to greedy what's the first character, and you try to minimize where's the first character. And yeah, you basically check if you can start with A, right, or whatever is smallest here, or let's say code. So you can start with C, right? If you can start with C, doesn't matter what's the rest. If you can start with C, then you always want to start with C, right? Doesn't, even though it makes the later characters less optimal, it's fine, because whenever you compare string, you always compare the first character first. Okay. So using that idea, we can construct this simple code. I can show you my code here. Basically, since the constraint is small, 100, my solution is, I think, 100 to the power of 4 or something like that. It's quite expensive, but since the constraint is small, you can basically do whatever you want. Basically, we first sort the first string. Yeah, and that is the answer, as we mentioned before, because we want greedy. And then for the rest of the string, we actually want to try each characters. Let's try starting with C. And when you start with C, you can sort the rest of the characters in decreasing order. So here becomes COED, right? And then you check whether COED is greater than or equal to the previous character, the previous string, right? If it is, then you can start with C, and if it's not, then you continue trying to start with D instead, and so on, right? So yeah, so that is how to solve this problem. And yeah, actually you can optimize this very very heavily, because yeah, if the previous string starts with B, let's say, then you know that if you start with C, you don't need to sort the rest of the string in decreasing order. You know that it's possible. And similarly, if the previous string starts with D, then if the next string starts with C, then you don't need to compare the rest of the rest of the characters as well. So you can optimize that part. But yeah, it doesn't matter because constraint is small. Okay, so yeah, and then if it's not possible at some point to generate a string that is more than the previous string, then you know it's impossible, because the way you do this, you always try to maximize the number of possible strings for the future strings. Okay, so yeah, let's not take too much time on this, because this is based on the order and the points, and and I agree that it is the easiest task. So yeah, we can go through it quickly. Okay, this and then the next task is actually quite interesting, because I don't know whether I overlook a simple solution, but my solution is quite complicated, and yeah, it has a number of points of the first one, so I thought it shouldn't be that complicated, but I ended up come up with a complicated solution. Maybe you can share your solution if you have simpler ones. But yeah, let's go through the problem. So basically the question is like there is like a number line, or like a long street or something, and at some points there are, basically there are like, the story says about vaccines. So here there are five type of vaccines, five kind of vaccines, five vaccines basically, right? And then for each vaccine, you are given where you have to pick up and where you have to drop, right? And the robot here, not you, but the robot will move within the number line, let's say, and every time it moves, when it picks up, when it goes to a vaccine pickup location, it will pick up the vaccine. And if it goes through a drop-off point and you have picked up that vaccine, that kind of vaccine before, you have to drop the vaccine there, right? So, and then the movement is, and then there can be 10 to the power of 5 movements, and each movement is like go right X steps or go left X steps, right? So yeah, of course naive solution will not work here if you try to increment your position one by one, because each move can be 10 to the power of 9 steps. So you won't be able to do that. Wait, let me check something here. Something is wrong with the stream. Give me a moment. Okay, let's continue. Sorry about that. Yep, okay. Now should be good. Okay, yeah. So, and then the question is, for each of the move, they ask you to print how many vaccines you drop on that move, right? So you have to print m numbers, where m is the number of movements, and for each movement you have to print how many vaccines you drop at that move, right? And you have to make sure that basically you can only drop a vaccine if you have already pick it up, which kind of makes sense, right? So yeah, my solution here is, I don't know what's the editorial. Maybe we can quickly take a look at the editorial. Yeah, it's probably similar, but yeah. So yeah, basically, for each vaccine. So my loop is not for each movement, but I try to iterate through all the vaccines, and for each vaccines, I try to find out which move picks up the vaccine and which move drops the vaccine, right? So, and then for each of the, yeah, and then because I know which move drop the vaccine, I can just increment the answer for that move, right? Maintain two sets. Okay. Of vaccines you haven't pick and vaccines you pick up but not this. Yeah, okay. I did not do that. Ah, okay, yeah. So yeah, that okay, then probably it's completely different then. Because if you maintain two sets, you will iterate through all the movements, right? And not the vaccines. Yeah. So again, my solution is I try to iterate all the vaccines, and for each vaccine I try to find out which move is the first is the move that you pick up the vaccine, and which move is you drop the vaccine, right? And yeah, which move you pick up the vaccine is quite easy, because you just try to, yeah, if you plot for each movement, you know where the robot ends up, right? You can plot that, right, where the robot ends up. And you can also create like a prefix max of the robot drop off points. So yeah, basically like okay, maybe we can draw something here. So yeah, let's say this example. So we know that the first move go to like let's say, I don't know, 1 2 3 4 5 6. So first move goes to 6, and then second move goes to 4, and then third move go to like 2, let's say, and then fourth move go to like 10, for example. Okay, if you create a prefix max of this, let's say 6 6 6 10. Okay, if you want to find the first move that picks up the vaccine, you can binary search this array to find out which is the first element that is greater than equal of the pickup point, right? Let's say the vaccine is at x equals 8, then you know that this is the move that picks up the vaccine, because all previous moves does not exceed x equals 8, right? So you know that this is the pickup point, right? And then after the pickup point, you want to check which move drops the vaccine, right? Of course, if you binary search and you don't find any I such that this suffix prefix max I is greater than x, then it means you never pick up the vaccine at all. Then you can just ignore this vaccine, right? But then once you know that, let's say, okay, let's write some more stuff here. Okay, let's say after 10 it goes to 12 and 14, and let's say the vaccine pickup point at x equals 8, then you know that this is the pickup. And then you want to find out, and let's say the pickup point is sorry, the drop off point dx is 16. Again, you want to binary search but starting from here. So you want to binary search from here, and now you cannot use prefix max at all, because yeah, it might be the case that you have already gone to 16 before. Like, let's say the move are like 6 16 10 12. If you, no, sorry, at this point you already pick up the vaccine, but okay, this is only the case if you go left, I guess. Yeah, so for going right is simple, but let's say the drop off point is to the left of the pickup, right? Then it's a bit complicated, because you have to, now instead of finding the max, you're finding the min, right? But you only find the min starting from the pickup. So let's say, yeah, let's say here, and then let's say at the end you go to 2, right? Okay, so let's say this is the moves, right? From 0 to 6 to 4 to 2 to 10 to 12 to 14 to 2, right? Okay. Yeah, and then let's say the pickup is at 8, and the drop off is at 6, let's say. Yeah, basically, since you know this is the move that picks up the vaccine, then you want to binary search from here, and you want to take the minimum of all these elements, right? And to figure out the minimum of subarray, you can use like segment tree or something like that. And yeah, basically you binary search, find the one that the minimum of this subrange is smaller than 6, right? Smaller than or equal to 6. Yeah, this is why I mentioned that my solution might be too complicated, because I use like segment tree to solve this problem. But yeah, turns out you probably don't need to. I try to iterate through the movements and keep a set of which vaccines have been picked up or not. But yeah, I ended up not coming up with a fast solution, with a solution quickly. So, and in the end, this solution came up to me. So yeah, I just decided to code this. Yeah. The code is actually not that complicated once you copy the library of segmentary using like Edcoder library or what. Yeah, it's actually not so complicated. Um, okay. Um, okay, let's move to the next problem. When iterating and using sets, you binary search for start of. I see. Yeah. Okay. Mm-hmm. Binary search for start of relevant points. Okay. Yeah. Because you use set, you can do set dot lower bound to find. Yeah. Okay. Uh-huh. Okay. Oh, so the set is sorted by the x value. Yeah. The set is sorted by x value. Okay. Yeah. I see. Yeah, that makes sense. Yeah. Okay. Yeah, that works as well, and probably that is the intended solution. Mine is a bit overkill. Yeah. Yeah. Basically, just like simulating the move. Um. Yeah, simulating the move, but you basically for each move you try to find which vaccines are pick up and drop. Yeah. So yeah, you kind of simulating. So basically, do what the problem says, but you don't like increment x one by one, which is kind of more natural solution, I guess. Yeah. Okay. So next problem. Yeah. Next problem is yeah, this evolutionary algorithm where basically there is a tree, a rooted tree, and yeah, basically we want to find triplets such that this basically, right? You don't really need to read this, but you want to find a triplet such as this. The rest of the paragraph is like natural. It defines what an ancestor is and so what, and but it's just a common definition basically, right? Basically, this is the important paragraph, right? So we want to find a triplet such that A is in the subtree of B, C is not in the subtree of B, and this satisfies, right? And yeah, basically each node in the subtree has some value, right? Yeah, and basically the way we can solve this problem is that yeah, we can iterate the node B instead, and because there is like max of SA and SC, we can kind of change this to something like where's my Jamboard? Okay, because it says SB is greater than K times max of SA and SC. We can change it to like two conditions, basically not max, basically K times SA and SB must be also greater than K times SC, right? This is basically, these two are equivalent, right? So because we managed to convert it to two conditions like this, we can find A and C independently, right? So yeah, we have to find A such that SA is less than SB divided by K, and we want to find C such that SC is less than SB divided by K, right? And once we know how many A and how many C's, we can multiply them because of a multiplication rule, right? Just yeah, it's quite simple actually. So yeah, because yeah, whatever values you want for you choose for A, it doesn't affect whether a value of C is possible or not. Yeah, it's independent. These two are independent conditions, right? Yeah, so now it becomes a data structure question where basically if like let's say we have a tree, right, and this is node B, you want to find how many nodes in this subtree that has this value, right? Okay, and yeah, there are various solutions to this. This is a classic problem if it's in a subarray. If you want to find if let's say you are given an array, if there is a query between these two between these two ranges, or in other words, in this subarray, how many elements are less than s, right? That is a classic problem. You can solve it with like merge sort segment tree or persistent segment tree or whatever, right? Yeah, I don't know whether you want me to cover it now, but I guess you can just read up, right? It's a very classical problem. I think in SPOJ there's this MKTH num. It's slightly different because I think the question is in a sub range, what is the kth element, right? Yeah, what will be the kth number in Aij segment? But it's essentially the same thing. If you probably add another factor of log, but if you can find what's the kth element, then you can also do like how many elements are less than s, or like if you want to put s in a sorted array, it becomes which element, right? What's the if s is the kth element, what's the k, right? Yeah, so it's essentially the same thing, and it's a very classical problem. And yeah, I unfortunately I ended up using persistent segment tree because in time complexity wise, I think that's the fastest. It has only one log factor. If you use some other data structures, you might end up with log square or log cube, or yeah, or maybe if you even have binary search on top of it, then you can get log 4, in which at some point it becomes slower than quadratic, so you have to be careful as well. But yeah, I ended up choosing persistent segment tree because I know the log factor is small, the log exponentiation of the log is small. But yeah, I got memory limit exceeded instead. Yeah, I guess with persistent segment tree, sometimes you have to be careful to clear up all these nodes that you don't, because we use pointers, and yeah, C++ does not automatically garbage collect if you, even though there's an object that is not pointed anymore. And yeah, because this object points to other objects as well, and if the reference of this object is like destroyed, like you don't point to these objects anymore, you should have cleaned up all of the objects that is pointed to it, pointed from it as well. Otherwise you end up with a lot of garbage that is still counted to the memories, right? Actually, it's quite of surprised me because there's 2 gigabytes. I don't know whether my solution actually takes that. Oh, there's 100 queries. Okay, so if 100 queries all if like this big, then yeah, it probably will take up a lot of memory. Yeah, if even if I don't garbage collect, if I just clear all of the memory every queries, right? If I don't, yeah, every queries I just clear up all of the, yeah, I mean, I still have the garbage collect, but I don't need to like, yeah, I don't know what I'm saying. Yeah, I guess I have to clean up every now and then. But I guess what I'm saying is that if there's only one test case, this would probably work. So I could have just clear up every n of queries. I don't need to clear up like cleverly, I guess. Yeah. So yeah, but yeah, there are 100 queries. This can be big. Yeah, probably it can take 2 gigabytes. Uh, okay. Oh well. Yeah, it doesn't change my rank much, but yeah, it's a bit unfortunate. But yeah, theoretically, like algorithmically, this is how you solve the problems. And implementation wise, there are various ways you can implement the classic problem just now. And oh yeah, sorry, because I covered if this is in a sub array. Yeah, in the sub tree, it's a very classic technique as well that you can consider like the time. So basically you consider the DFS order, like the pre-order of these nodes. So basically you DFS using pre-order. So pre-order means that this node is counted like 1, and then this is 2, 3, 4, and so on, right? And then for each node you keep what is the pre-order of that node and the maximum pre-order node in the subtree, right? Let's say this is 6, then you know that you can change this query to like 2 to 6, because you know that all the nodes having pre-order time, let's say index or time outside 2 and 6 is outside this subtree, and all the nodes inside between 2 and 6 pre-order node is inside this subtree. So yeah, you can convert subtree problems to subarray problems. It's essentially the same in this case. Yeah. Yeah, so that's how I implement this problem. Yeah, I use persistent segment tree and all these pointers stuff. Yeah. And oh yeah, because s can be huge, yeah, you need to compress the s. You can do that. Okay. I haven't read the chat. Let me read. So, trying to combine data structures, we can answer how many elements there are less than s, and you use strip. Yeah, there are. Switch the order. Switch the order to the elements itself. Probably still use the same amount of memory, no? Because it's essentially the same number, and the dimensions are both n. Of course, we try to compress this as we don't use 10 power of 9. I don't use 10 power of 9. Oh yeah, actually with persistent segment tree, you probably don't need to compress. It will just use more memory. But for me, I actually compressed it. So yeah, now both dimensions are n. Even though if I reverse the dimensions, I think the memory usage should still be the same. Oh, I see. Yeah. Okay. Yeah. Oh, yeah. But that will take more log factor. Yeah, I was thinking of implementing this solution as well, like using merging smallest to largest. Yeah, so in that sense, you won't need persistent data structure, because like yeah, you can basically, because in persistent, the idea of using persistent is that you can solve this query and later solve this query independently, and then you can go back to solve this query again. But you actually don't need to if you can answer the queries in the order, in any order you want. Yeah. Think, yeah, you actually don't need persistent data structure here, and then yeah, you can actually keep the data structure in this node and in this node, and then when you combine and when you go up, you can take the one that is largest and then combine it with the one that is smaller, right? But then you will lose the data structure on the child, which is fine. You don't need it anymore, right? Yeah, you don't need it anymore. Yeah, so you can probably do that as well. I was thinking of implementing this actually to avoid all the ugly persistent segment tree crap, but yeah, I was worried with the extra log factor, which I shouldn't probably, because Google CodeGem usually have generous time limits, so I shouldn't probably worried about time limit a lot. Yeah. Yeah, so yeah, I think you can do that. So you can just have a segment tree, standard segment tree, that counts the number of elements less than si. So the dimensions of the segment tree is the number of distinct s values. And then yeah, you update them with the small to large merging. I think that should be possible. Yeah, I was thinking about this solution as well. Oh well, yeah. Yeah. Any solution works. Again, there are many solutions, many ways you can solve this classic query of like how many elements less than s thing. So yeah. Okay, so that's how you solve this problem. I will try to, maybe should we try to, okay, we can maybe do it together. Yeah. Let me know if the text is a bit too small on my editor, but yeah, let's see quickly. It should be quick. We try to garbage collect this all these pointers. Yeah. Um, Basically, yeah. X, we need to if x left is not null, we first erase x left, and then x right, and then we delete x. Yeah. And then at the end of the query, we should be able to erase all this stuff, right? Yeah. Strap in erase sti and see whether this helps with the memory limit issue. Why is the code not printing anything? Oh, because I'm in the wrong directory. Oh, of course. I got segmentation fault. Um, can you do this? Comes now. Mm, how do you? Why does this doesn't work? Huh. Um. Okay. I can't do this. How should I? Okay, never mind. Okay. I'll try do it later. Okay. Next. Problem D. Okay. Yeah, I feel like this problem is okay. It has the same total points as the previous one. The way that it has more subtasks in some sense makes it like looks like it's harder than the previous task. But actually the total points is the same. And yeah, I feel like this task is not harder. It well it's more interesting actually. It requires more novel idea. So yeah, maybe you can argue that this is more difficult, but it's not that complicated actually, the idea. Okay, so this task, yeah, basically like you are given a graph and each edge has a color, like let's say a color, um, and then there are several queries, and you want to create a path from u to v, like each query has two nodes u and v, or s to t, let's say. Each each query has a node s to t, and you want to create a path, and it's actually not a path, even though this problem statement uses a path, but path is in graph terminology is well defined, right? It's a commonly agreed term that path should not repeat nodes, right? So yeah, it's actually a bad use of the term path here, because in this problem you can actually use several nodes and edges multiple times, so you can go in a cycle several times. Yeah, I think the more common correct terminologies for this is tour. There is a tour and a walk. I forget which one is which, but yeah. Basically, yeah. This problem says you can repeat many nodes, many edges, as many as you want, and the question is you want to create a tour, um, or walk, uh, such that the number of different colors that you go through on these edges are an odd number, right? So yeah, that is the question, right? And yeah, the question is it possible or not to go from s to t? You can repeat nodes, you can repeat edges, such that the number of different colors is an odd number, right? And here in this problem, actually the fact that you can repeat the path can repeat nodes and edges is important. Otherwise, I don't know how to solve it. Okay, so yeah, basically so yeah, without the colors, this is a classic problem. If there's no color, you just want to check whether there's a path from U to V. You can, yeah, there's many solutions. You can use union find disjoint set, or you can just run DFS and forms connected component. And then the question is just whether U and V belongs to the same connected component, right? Okay, but then there's this color. So my solution goes in like two steps. First, if so construct the union find disjoint set as usual, and for each component you also store how many distinct number of edges are there in that connected component, right? And if U and V belongs to the same connected component and the number of colors in that connected component are odd, then you confirm can go, right? Because yeah, again, this is the important part, because if you can repeat nodes and edges, that means you can go through all the edges in that connected component. Even though, yeah, even though like let's say this is the connected component. Even though this is S and this is T, you can go through all the edges here and then go back here. And basically you can, if there is a large connected component, you can go through all the edges in this connected component, right? Okay. So if these connected components have if the number of colors is odd, then it's done. You can obviously go from S to T, satisfying the constraint, right? Because you can go through all the colors in this connected component, right? Now the tricky part is if this is even, then you want to try to avoid using one of the color. If you can avoid using one of the color, then it becomes odd again, right? If you can. Now, so basically my solution checks for each color, because there's only 100 colors. I try to remove one of the color in this connected component and see whether S and T is still connected, right? So yeah, that's basically it. If I can remove one color from this connected component and S and T is still connected, then it's possible, okay? And yeah, because number of colors is small, we can basically create a union find disjoint set for all kind of colors removed. So yeah, basically I have like this union find disjoint set. The parent I is like the UFDS when edge I is removed, edge of color I is removed, right? So we can pre-compute that, and of course we also have like parent 0 is UFDS when no edge is removed, right? So yeah, we want to have the full graph as well, so that we can answer the first part of the problem where whether U and V is connected in the first place, and yeah, you can also have some attributes here to find out these components, whether a color C is present in this component, is in this Boolean array. Yeah, basically this tells whether this color is present in this component. Yeah, and then once you figure out that U and V belongs to the same component, but there is actually even number of colors in that component, you want to try removing each color, right? And because I have this joint set, I can do it easily, right? Yeah, so that is my solution to this problem. And yeah, it's actually quite yeah, you don't require sophisticated data structure or techniques, but yeah, the idea is quite novel. I don't know whether this is the intended solution. Let's see whether I can read this quickly. Yeah, I think it's similar. They build K+1 graphs. Yeah, and there is like proofs and stuff. Um, yeah, I just realized now when I read this stuff, uh, that I didn't I didn't consider when, let's say, I remove some edge. Um, so yeah. Let's say we try to remove color I, okay, and we know that S and T is still connected without color I. Yeah, I thought I can just simply say that now this is possible because like I can avoid color I, so now the number of colors decrease by one, right? So that becomes an odd number, right? But I didn't consider that some of other colors might be uh, unvisited, right? Because let's say this is I and this is J. Now if I remove I, J is no longer traversable as well, right? So now actually the number of colors decrement by 2, right? Yeah, I actually didn't think of this during the contest. I just realized this now. But I guess this still works because you can actually remove J instead, right? So and then the thing still works, right? So you can, like, if there is like a color that blocks another color, then it just works out fine when you consider this node instead, right? So, and yeah, I guess what happen if there's a J here? Okay, that's probably okay. Maybe it's not. Okay, this is weird now. Okay. Wait. Does it mean my solution is wrong? Um. Oh, no, no, no. This color must be unique, right? Because if this is J and there's a J here as well, then by removing this edge, you can still visit J. So this is no problem. The problem is only if this edge does not appear elsewhere, right? Because if this edge appears elsewhere, then by destroying this, you still can visit color J, right? Yeah, so that's fine. Okay, so yeah, this is fine. Yeah, but yeah, yeah. So yeah, basically, yeah, for ST query, I try to check whether this color appears in the connected component of SNT. Oh, first of all, I check whether the SNT belongs to the same connected component. If not, then they obviously cannot be fulfilled, the query. If it is, then I check which of the what are the colors that belongs to this connected component, like that is like present in this connected component, and then I increment it, and then if it is odd, then I know that it's you can obviously visit you can obviously fulfill the query. Okay, and then otherwise you try to remove one color and check whether SNT is still connected. Okay, yeah. Okay, sorry, does that answer the questions? I'm not sure which proof you are asking, Edward. Okay, yeah. Okay, but yeah, let's move on. Let's continue to the final task of the contest. Yeah, this is annoying actually. Like, I don't know whether it's intended or not, but my solution is is not fun to code. It's pretty long because it considers many different cases. Um, yeah. If I Yeah, maybe we can go back quickly. If I read this quickly, I think it's basically this. No, probably not. Uh, yes. Okay. Uh-huh. Okay, it's probably a bit different. than the analysis. Will always be connected after removing edges with those. Okay. Yeah, it's a bit different. This part is different than my solution. Oh wait, you can find a climate and just yeah, I don't know, I need to read the terminologies as well. But yeah, again, my solution is just in this part, like if the number of colors in the in that connected component is even, then I try to just remove one color. And if removing one color still connects S and T, then it's possible to connect to. Then the answer of the query is yes, basically. Yeah, that was my solution. Okay. Um. Okay, and then yeah, for problem E, so the question is similar to the first one, except that you now have to construct the partitions. Yeah, this is why the problem says has to split PS into P substrings, because that is exactly the question for this problem. Sorry. Yeah, so for this problem, you actually have to cut such that after the cut, if you give it to the first problem, the answer is always impossible. Right? Basically, after the cuts, you want to make sure that after the cuts, you want to make sure that there is no way to rearrange each of the cuts such that each cut is increasing, right? Basically. Okay, yeah. Yeah, the feasible subtask, I guess you can brute force it. You can do 100 times to the power of 2, try every possible positions of cuts, but yeah, it's not fun. It's not interesting at all. It's just brute force. Yeah, and then for the large one, yeah, basically I try to find cases, basically, right? And yeah, I don't know whether the analysis, I can imagine the analysis will be long to cover all of these possible cases, except if I overlook something, right? But yeah, first of all, if n equals p, I need to handle this separately, because for this case, I assume that n is longer than p, the string is longer than partitions. But if n equals to p, this is actually quite straightforward, right? Because n equals p means you have to cut at every possible positions. That means there's only one possible solution, and you can just check that solution, right? And that solution you can just simply check if if there's a position where it's greater than si plus 1, because after you cut at all possible positions, you give it to, what's the name here, Badari also doesn't have many choices as well, doesn't have any choice at all, right? Because each string is just one character, there's no way to shuffle that character, right? So yeah, and then then it becomes just checking whether each cut, when concatenated, like the string itself, is a increasing, like the characters and increasing or not, right? So yeah, if it's not, then it's actually good news for you, because you can make Badari suffer, right? Yeah, so either possible. Otherwise, if the string is already sorted at the beginning, then there is no way for you, right? Impossible, right? This this part is not true. So it's not true for p less than n. So the annoying thing about lexicographical string is that z is smaller than zz, right? So or whatever characters, right? A is, so basically any prefix is smaller, right? So even though the string is increasing, like this query, right? Like this example, right? You might have think that, oh, there's no way this is possible if the string is non-decreasing, right? But if there is 3 of the same letters, right? You can actually, this is actually possible if p is less than n, right? Because you can cut like right here, and then there's no solution to this query, right? Because you cannot shuffle this, and a is actually greater than a, right? So this is impossible to solve, right? So you can actually cut here and here. So yeah, if p is less than n and greater than 4, then if there is any three of the same letter, you can always do this. This is always possible, because if there's three of the same letter, you can cut here like this, and then the rest, it doesn't matter how you cut here. That is why you need at least p at least 4, right? Okay, because yeah, from this you already cut 2, and then here this is at least 4, right? If p is 3, you cannot do this, right? So if p is at least 4 and p is less than n, because if p equals n, then you have to cut here as well. So if p equals n, you cannot do this. So if p is less than n and p is at least 4, then if there is 3 of the same letter, you can do this, regardless of what the rest of the characters are, right? And if there is no such 3 characters of the same thing, you can always fall back to the approach of p equals n, where if there is a si greater than si plus 1, you can make individual character of this as well. So let's say there is like a, b, c, d, d, e, and then d, f, g. Then you can cut here, and then cut here, and then this will be impossible, right? And then the rest doesn't matter, right? So yes, the solution for p greater than 4 is actually simple. P at least 4 is actually simple, because you can just look whether there is 3 characters of the same, 3 characters, 3 I plus 1, I plus 2 with the same characters, and if there is a decrease as well, right? Then it's very easy in these cases. Otherwise, then the string can only be like, the worst case is something like this, right? It's increasing, and there is no 3 position of the same character, right? And in this case, no matter how hard you try, it's not hard to see that it is impossible for you to cut to make the reshuffle, right? So yeah, so for p greater than 4, greater than or equal to 4, so if p is greater than or equal to 4 for large p here, I just consider these 2 cases. If there is an si greater than si plus 1, or there is a 3 consecutive characters, otherwise it's impossible. It's the sample actually helps as well, because the sample is in that format, except that CND is only 1, but yeah, the sample is like in this format, where there is no 3 characters of the same and there is no decreasing characters. Yeah, you can see that yeah, this probably is impossible, and indeed it's impossible, right? Yeah, because you cannot make these cuts, right? So each cut can like this, like, yeah, you can, if you cut here, then it's obviously larger than this and smaller than this, so on, right? So yeah, there's no way you can cut this, right? So yeah, okay, so that solves p larger than 4, right? Now for p smaller than 3, this is actually smaller than or equal to 3. This is actually the complicated part, ironically, right? Usually if the value is bigger, then it's hard, but in this case it's actually the other way around, and yeah, it's actually, so in some sense, for this problem, the feasible, the smaller test set is actually the harder one, if the length of s can be long, right? So yeah, it's because of the length of s here is small, then it's actually easy. But if the length of s here is 10 to the power 5, then this test set 1 is actually the harder part of the problem, right? Yeah. Okay. Yeah. Again, I don't know whether I overlook a simpler solution or not, but my solution for p equals to 3 in particular is very, very complicated. Yeah, let's go to p equals to 2 first. Yeah, p equals to 2 is actually quite simple, because you can just brute force the cutting point. Of course, you cannot. Well, if you know where's the cutting point, right? Let's say this is the string. Where is my pen? Okay. Why I cannot write anything? Okay. okay, let's say this is the string. If you know the cutting point, let's focus on p equals to 2. Then you know that you can just simply check again using the greedy solution. You can just simply check if you sort this in increasing order, and then you sort this in decreasing order, decreasing, and then this is increasing. Okay, if S1 after you sort is greater than S2, then this is good news for you, right? Because if you already sort this, if you already compute the minimum possible value of this, and you already compute the maximum value of this, and still this is larger, the minimum of this is larger than this, then it's a good news for you. You can construct the solution, right? Then basically there's no way this is smaller than this, right? Because we already minimize this, we already maximize this, and so on, right? So yeah, except that we cannot really sort because we already try to cut at every possible positions. If you again sort and compare the string naively, that will become n square, right? So so yeah, basically the smart way to do this is you just find what's the um, maximum character, the largest character in this. Sorry, no, the minimum character in this. So yeah, usually it's a, right? But yeah, basically in this partition, what's the smallest character? What's the character with lowest SG value? And then in here maximum, right? And if the lowest character in here is greater than the largest character here, then it's impossible, right? If it's the same, there is a bit of a tricky thing where you have to count the number of occurrences and stuff. So yeah, it's basically, yeah, if this is larger, you know that you can construct a solution immediately. But if it's not, then yeah, you have to count how many characters are there, and if this has more characters than this, like the character that is equal, yeah, it's you can consider the cases, but it's not too complicated. Basically, you consider how many, like let's say the the smallest, sorry, yeah, the smallest character here is n, so like this is n for example, and then you cut to like n a, something like that. And in this case, the largest character here is n, and the smallest character here is n. It's the same. You count how many here. If here we have more n's than here, then we confirm can cut here as well, because zzz is greater than nnaa, something like that. So you count how many such characters, and yeah, if it's more or equal, then you confirm can, except if it's a prefix, right? So if you just have nn and you have nna, then in this case nn is actually smaller, so it's you cannot cut here, and so on, right? But yeah, it's not too complicated. The solution for p equals to 2 is not so complicated. You can just brute force the cutting point, and for each cutting point you just do a more clever method of checking whether this cutting point valids or not, right? And then for p equals to 3 is the main part. Let's check the yeah, exactly the same thing, right? So the editorial also says that p equals to 3 is the hardest part of the problem. Okay, yeah, okay. Oh, there is actually two approaches mentioned in the editorial, and here in the first approach, they actually left the larger p aside. Interesting. Okay. Okay. But yeah, in this problem, they say that p, in this solution, they say p equals to 3 status. Okay, so yeah, let's go to p equals to 3 now. I hope you're still with me. Let's see. Yeah, so here p equals to 3. My solution is a bit long. But yeah, first I try to cover the obvious cases where if some of these cases are true, then we can construct the solution, right? And then we consider what's the rest of the cases. Like, okay, first of all, hey, good morning. Yeah, it's actually evening here in Singapore, 3 a.m. Well, 3 a.m. is it's not evening, it's dawn. Okay. Yeah, whatever. Okay. Yeah. So p equals to 3, right? Technically morning, true. Um, I don't know why I'm streaming at this hour. Maybe I shouldn't, but oh well. Okay. Okay. P equals to 3. So the first condition that I check is whether the first character is the smallest character in the string. Okay. So I guess let's assume for convenience that the string every character between A to Z is present for convenience, right? So whenever smallest character, whenever I say A, it doesn't have to be actually A. It's basically the smallest character that appears in the string, yeah. But yeah, I guess yeah, that's what I'm saying. Um, yeah, if the first character is not A, let's say B, right? Then this is also good news because we can immediately construct the solution because let's say the A is here, then we know that we can make this cut, right? And it is now impossible because there's no A here, means that yeah, obviously this is larger than this, right? Okay, so yeah, so if this is not A, if S0 is not A, then this is done, right? And similarly, if S n minus 1 is not Z, this is also done. Okay, because if this is not Z, then yeah, then let's say the Z is here, and let's say this is the rightmost Z. Okay, so if the Z, there are several Z here, then yeah, we can cut here. Okay, and we know that this is larger than this, right? This is larger than this because there's no Z here, right? So yeah, this is the simpler cases, and then yeah, and then the rest is a bit annoying. Okay, and then yeah, okay, so we know that the first and the last character is the smallest, and in this case there is actually no solution, almost, except in a very annoying case where so yeah, basically now the rest of the cases is we consider that the first character is A and the last character is Z, and yeah, basically oh, there is another thing. If in the middle there's another A as well, then this is actually done as well because we can cut something like this, right? And we know that this is larger than this, right? Because A is a prefix of whatever is in here, and we know that a prefix is smaller than the rest of the string, right? So if there is A in the middle, this is done as well. So like if Si is A, this is done for I greater than something, greater than 0. Okay, so the first character have to be A, the last character have to be Z, and there cannot be A in the middle. If it's the second character is still fine. So this is actually I greater than 1, right? Okay, yeah, and then the remaining case is actually impossible except for a very annoying case. AZ, yeah, okay, yeah, this is what we want to focus, yeah. So if these three are false, yeah, so we know that this is A, this is Z. Okay, yeah, so yeah, this is on most cases this is impossible, and the reason is that let's say you cut here, okay, and cut here, okay, okay, and assume there is no Z here, let's say no Z. Okay, then this is not a valid cut. Okay, why? Because yeah, you know that you can construct a string that is A here, and you can construct a string that is Z here, and here there is no A. Okay, we know no A. So yeah, this cut is bad, right? This cut is bad, right? Because no, let's say not C. Okay, yeah. So the only possible cuts that you can make is if all of these contain Z's. Okay, because if there is E here, then we can start with E, and this is okay, right? So the only cuts that you can make is when this middle part only consists of Z's, and the number of Z's here is more than the number of Z's here. Yeah, that's the only cut that you can make. Yeah, so that is the solution basically, right? So for all these cases are done, and for the rest of the cases, you want to find a cut such that you want to find a cut such that in the middle portion only contains Z's, and the number of Z's is more than the number of Z's here. And this is now okay, because yeah, here now this Z's is greater than the maximum that you can construct here, right? Otherwise, because if there is other characters here, let's say E, yeah, let me mention once again. If there is a E character here, then this middle part we can construct starting from E, and that means this cut is bad, because we know that we can construct starting from A on this one, and we know that we can construct starting from Z on this one. Then this cut is bad, because we can sort. Then Badari has a choice here, right? Yeah, and yeah, so that's the solution basically. So I try to loop through the string and keep track how many consecutive Z's that I have figured, and if the remaining number of Z's is smaller than the number of consecutive Z's that I saw, then I can cut there, right? Yeah, so that is the solution here, this part. And I actually realized this late. So previously I don't have this case. My code is basically this, but then yeah, I submitted and then it fails on the test set one. This WA is because I didn't consider that case. And then yeah, basically then I realized that I need to have this as well. That this case is actually makes it possible, right? So yeah, basically if I keep track, so besar is the largest character in this string. Yeah, I count if SI is largest character of the string, I increment the number of consecutive Z's that I have seen. And if it's now bigger than the number of Z's that is left in the string, then I can actually construct the solution. Yeah, it's very annoying problem. Yeah, and yeah, it's not usually the case that the hardest problem of the contest is a ad hoc problem, but yeah, it's actually it doesn't require any technique at all. I guess I guess you have to familiar that some string gotchas that like you can actually that like ZZZ with p equals to 2 is actually valid, is a possible case, because you can cut here. Yeah, basically, even though this looks impossible, but you have to remember that every prefix is smaller than the longer string, right? So yeah, but yeah, otherwise, yeah, it's a very ad hoc problem. You don't need data structures or like any techniques at all. Yeah, so that is my solution. Of course, there especially with this kind of constructive problems, there can be many solutions. Yeah, so uh yeah, I guess the analysis also like covers cases basically, right? Considers many cases, which yeah, it kind of makes sense for this problem. um okay, so yeah, um yeah, so this is the tasks. Yeah, I feel like this kinds of fit with what they're trying to do for problem C in the FAQ. They say it's between round 2 and round 3. I feel like probably it's slightly easier. But yeah, it's about the correct difficulty. This is easier than round 3. Um, it's probably more of like round 2 problems. So probably not harder than round 2, but just like round 2. Um, well, there are more problems than usual round 2, but there are more hours as well. Round 2 usually is 3 hours. This one is 4 hours. So yeah. Um, okay. Yeah. Yeah. Actually, finished the contest a bit early. So of course, I didn't know that I didn't solve this C large because of memory issue. But yeah, I finished the contest in 3 hours and 10 minutes. So I decided to take a look at some of other contests, and I didn't have much chance to read other tasks, but I actually take a look at this easiest task of what they promoted, that they intended to be almost finals problems, like harder than round 3 but easier than finals. Um, yeah, and yeah, this is not actually too complicated. I don't know whether people want to listen to my explanation to this task. Yeah, maybe I can cover it quickly. So, um, yeah, I should probably say that this is easier than some of the hardest tasks in problem C, in round C, which probably they intend to as well. Some of these tasks are like overlap. Like the easiest task of round D is probably easier than the hardest task in round C. But yeah, if you guys want to take a look at this problem, this is actually not so hard problem as well. Um, yeah. Yeah. So yeah, and I solve it during the contest. But yeah, it takes me 3 hours more, of course. So my rank in this contest is not that good. But yeah, I just want to try to solve this problem. Um, okay. Yeah, but otherwise that should be all for the round C task discussions. Maybe yeah, once I if I have time and I can solve some of the more of the problems in round D, we can have another this kind of discussions for round D. But otherwise, yeah, for round C, that's all. Let's see what the analysis is for problem C. Um, yeah, it mentions segment tree. Um, yeah, and it uses the pre-order traversal as well. Um, huh. Oh, I see. Yeah, okay. This is actually interesting. Um, yeah, because we can we can query the data structure such that S is yeah we can actually query the node such that S is always increasing. Uh, so yeah, going back. Oh, I already cleared the page. But yeah, we want to find a node. We want to count how many nodes um, such that Si is smaller than SB per K, right? Okay. Yeah, if we query this with the increasing value of SB, then this is increasing as well. So if we, yeah, then we can have a segment tree, and the dimension of this segment tree is actually the nodes. So this is the nodes, right? And then whenever we increase this, and this is now greater than Si, we can update the ith value to 1, something like that, right? yeah, this is actually a better solution. Yeah. Uh, yeah, and you won't need a persistent segment tree. Yeah, I also want to cry in the corner because, yeah, my solution of try to compute this in any order of node B that I want cost me the like basically makes my solution more complicated and cost more memories to use persistent segment tree. Yeah, this is actually clever. Yeah. Okay. Um, yeah, and this problem also, my solution is overcomplicated. I could have just like simulated the move in like not really simulation, but like doing the move basically. But yeah, it uses very complicated solution. Whatever works. Okay. Yeah. Okay. That should be all. Thanks a lot, guys, for watching. Yeah, and yeah, see you all next time. Bye.